Hey, how you doing? Tech here. Who is that guy down there? Well, if you are a nerd, then you may recognize him from an older Nintendo game, which is old at this point because I don't know. I haven't played some of the more modern ones, like outside like the really modern ones. So I don't know if they may still be in there. I have no idea. So either way though, Pole's voice is a bad guy from a Nintendo game, the Legend of Zelda, the first ever Zelda. When this was before like round things existed in video games, and this bad guy in particular, the Japanese version of the game was kind of strange because, well, in the instruction manual for this game, it used to say that these creatures were did not like loud noises, which like nobody in America really, we're kids, we didn't know what they meant. Like the TV's listening to us, the game is listening to us. No, it wasn't. But as it turns out, the Japanese game did. The controllers used to have microphones on them, and I don't know this for a fact, but I believe what the way that you used to kill these bad guys, you take the Nintendo controller, the Japanese Nintendo controller, the whatever, the Famicom, I don't know what it's called, and you take it and you scream it, you go ah, and that would destroy these bunny-looking things. But they're called Pole's voices. So why is he on this circuit board? Because I built a circuit that I'm actually kind of working around with one of my classes with right now, to which the circuit uses the microphone that we explained in an earlier video. I'll kind of explain what the MEMS microphone is. It actually uses that MEMS microphone and lights up some LEDs. Depending on how loud the sound is that's actually going into it. A green one will light up for more of like a soft tone, like a whisper. A yellow LED will light up if there is a louder noise, and then a red LED will light up if there's like straight out yelling, is what it is. So we built a circuit board, and I kind of prototyped it out in the beginning just to make sure that I could kind of work with it for the most part. And we encourage all sorts of artistic flair when you're working around with circuit boards like this. It's really kind of a fun thing in a lot of ways. And so we actively made sure that the circuit board had. I made sure that the circuit board has some other stuff on it. In fact, the circuit board is not very big. It's about the size of a microscope slide, so it's a little bit around. I think it's like 2.5 inches by in length and 1 inch or so in width, like just barely under 1 inch. It has both a top part and a bottom part. And if one were to look very carefully at the bottom part, there is actually a complete scaled down version of the entire original Nintendo Legend of Zelda map. Like the first map just kind of shrunk down to the size of chip components. So if that ain't nerdy, I'm not quite sure what else could be nerdier than that. That's pretty nerdy. That's really nerdy. Yay! Well, anyway, we encourage our artistic interpretation with all the things that we build. So at the same time, I thought it'd be useful to kind of make a multi-part video in which we slowly assemble together this circuit and actually explain a little bit about how it works, both to kind of help my students out who are actually currently in the process of building this circuit, but also at the same exact time being able to just explain the basics of the circuit. Feel free to use this circuit. Use the parts within the circuit. I'll kind of go into a little bit of an explanation behind the whole thing with it here. So where is my schematic? Okay, so for people who are new to electronics, or kids who are watching this because I put a picture of a weird bunny-looking thing in the thumbnail, this weird-looking diagram that you're looking at right here is what we call a schematic. Now, a schematic is a drawing that shows how electronic parts are connected together, but doesn't necessarily show like where they're actually located on here. It tells us a little bit about the part, it tells us how it's connected together, and it represents this using a series of symbolic graphics that are representative of how things are actually put together. First, though, I would like to kind of explain even maybe a simpler part about this, like the block diagram based on how this whole thing works. This is something of my design. There are designers out there that if you see this, you might be like, oh my goodness, that's this could be working way better than that. And I'm not saying I'm an expert or anything like that. I'm an instructor. So if you have any constructive criticism towards what it is that's in this video, I'd be interested to hear it. So I'm sure some of the viewers would as well. Please be sure to comment in the parts below here what you think could be improvements or deprovements. Deprovement. Just break the thing, crying out loud. Anyway, the first part of the circuit consists of a 3-volt lithium-ion battery, which is actually connected over to the back there, and a control mechanism. In this case, a small toggle switch, not a toggle switch, a push-button switch, like a tactile switch. That when you hold the thing down, you hold the button down, that's what turns the whole thing on, and it has a little bit of a type of response associated with it there. Then there is this provides power to all the other parts of the circuit, and what we would call ground. People who are new in electronics, you've still probably at least heard of ground. It's very likely the thing that you have perhaps at some point stood on at some point. It represents a lot of things, but in the case of this circuit, it represents kind of like the lowest part of the energy, the lowest part of electronical energy that's on the inside. Electronical. Yeah, electronical. Boy, that's great. I'm really glad I caught that on the camera here. Electrical. It really represents the lowest form of electrical energy that it is. It's similar to height, right? Up high is what we call a 3V, 3 volts. That's what the battery, lithium battery, just regular lithium like a watch battery provides. And the ground is the lower part of the that voltage, as if we were like, if you were to compare someone like how tall is someone, they might be, 1.8 meters tall, for instance, but down, to they're measuring that in reference to the ground that they are, or whatever the thing that they happen to be standing on. That's what this ground happens to be as well. I remember in electronics, I was always confused about what ground is, and it's taken me a little bit of a while to make sure I figure out kind of what that is. But anyway, the next block on here has sound coming into the microphone circuit. The microphone uses 3 volts of power and a ground type connector coming over to here. Then there is a coupler circuit. Now, now that I'm noticing it right here, I am actually missing a grounded connection, which I'm going to maybe steal. Can I steal something? Can I take a wire from here? Maybe. Oh, maybe I can. I don't know if I can or not. Can I? Is that okay? Can I borrow you? Is that all right? Is that all right? There is actually a grounded connection on my circuit that goes down to what we call a coupler circuit. The purpose of the coupler circuit is to change the what we would call the DC bias, or basically change where the signal is in reference to where the ground happens to be. And basically the real purpose of it is to kick out any DC, any direct current, is what is the purpose of this. So we have a coupler filter circuit is what we have for this here. So it also filters out some of the noise, and that goes over to an amplifier. The amplifier changes the signal coming out of the microphone so that it is representative of a true varying DC signal at this point. Which then goes over to a circuit of what we call a comparator circuit. The comparator circuit compares the signals and will light up these LEDs. It compares the microphone signal coming into a dedicated electrical signal, and if one of them goes higher than the dedicated reference signal, which does not change no matter what, then the LEDs will turn on. But if the microphone is not loud enough producing a signal, these guys always stay where they're at, then the LEDs will remain off. And we set the references on the comparator likewise so that they can ultimately show a little bit about how we'll light up the LEDs in the correct way depending on what we set that reference to. All of this is provided using 3 volts coming off the lithium-ion battery and the control source, which controls everything turning on and off, and as well as the ground that shows what everything is in reference to. So this is a hobbyist type of circuit. It's a simple kind of multi-phase, or barely even that, like a several phase circuit is what it is. Kind of a fun little circuit though, is really kind of what it is. Okay, so I've actually got the circuit built up into little tiny blocks right here, and we're actually going to build some of these blocks step by step with it. I have at this point, actually I'm looking at this right now, and something seems like it's kind of a little bit wrong with the way I've built this circuit, but that's okay with it here. It's this capacitor is not doing what I wanted it to do. So there is a DC source that actually happens to be on the back of the circuit. There is a control switch that is this guy right here. That's going to be basically like when this switch is closed, it allows signals to pass from one side of the switch down to the other side and out through what we would call this net called VCC. A net is kind of a way of saying like somewhere else in the circuit, if these letters ever show up again and this symbol ever shows up again, there's actually a wire drawn across the circuit. This prevents me from having wires all over the place and having a spaghetti mess rat's nest of wires across the whole circuit. Some circuits do look like that. This circuit actually has a large amount of wires, so net lists and nets like this provide a little bit of some help in terms of being able to connect this. Now I actually have something here called R1 jumper. What a jumper resistor is there's meant to be, in case I need to bypass the switch to just permanently leave the thing on so long as the battery is connected to it, that jumper switch is there to have a basically a short resistor, an electronic device that opposes current. But in this case right there, it actually doesn't oppose almost any current whatsoever. It's pretty much just a piece of metal that we would connect across there, and that would prevent the switch from actually doing anything. It would it's a way for me to test with both my hands without having to have one thing that's always holding the switch down. More of a troubleshooting thing. So there's actually not going to be a component there, but on the circuit board there actually is room for a component there. This capacitor right here is what we would call a bypass capacitor, and I've technically put it in the wrong spot. I would really want to have this capacitor tied across the switch because there's a little bit of some mechanical motion that happens with the switch. I would actually want to have a capacitor there to basically sop up some of the static energy, if you will, of just having the button pushed over and over again. Since there's mechanical contact, there might be small bursts of surges coming into there, and the capacitor is going to take that while letting the rest of the smooth signal go all the way to the rest of the circuit. Is what that is. But having it tied across the battery doesn't really help me very much. I would rather have this wire connected all the way up to the top part of my switch so that it actually works with the switch. But that's okay. It'll still work plentiful fine right there. The next block, which we'll kind of work with today, a little bit with it today. The microphone is on here, which the microphone has 4 connections to it. It has 2 of them are ground. One of them is, well, it's called VDD, and there's various electrical nomenclatures. It's essentially power input, which if you were to look at it, is connected up here to VCC with that red dot right there. That red dot is what we would call a node. And a node is a party point for electricity. It's where multiple wires, by classic definition, it's 2 or more, but it's really more like 3 or more in most cases. 3 or more wires connect over at a point. So what that represents is an electrical connection of a green wire. Now that's actually connected to the C2 capacitor, which is tied down to ground, and this is here to help prevent the microphone from having any kind of problems in terms of it switching itself on and off while power is being delivered to it, and also helps to prevent any kind of surges from going into the microphone as well. It's what we call a bypass capacitor, and is there the 1U is the electronic value of capacitance, is a 1 microfarad capacitor is what that is. The last circuit, which is over here, by the way, the program that I use for this is an online cheapest free program called Easy EDA. Fantastic program in my opinion to be able to use. Highly recommend looking into it, and it's free. I've been using it for a few years now, and I've found it an excellent pedagogical tool to be able to teach people how to build schematics and layouts on the inside of there. As many as 4 layers is what I've personally done. I think it actually does a little bit more than that now that I'm thinking about it. Now on the end part of it here, the part that we're going to leave with the video today, there is a 1 microfarad capacitor that comes out through the output of the microphone, and the microphone, we aren't going to attach the microphone near last. In fact, probably the last 2 things that we're going to attach to the circuit are the microphone and the battery that's over here, and I'll explain why here in just a little bit, the battery and the microphone here. But the output, the last pin of the microphone, comes out to a 1 microfarad capacitor, and this 1 microfarad capacitor is going to be removing some of the DC elements of the output. What that means is, like, if this line right here is 0, my signal is actually veering around. Like, if I talk really quietly, it goes like this, but if I talk really loudly, it goes up and down like this. The capacitor basically moves it down to this axis right here, where talking really quietly goes like this, and talking really loudly goes up and down like this. Is essentially what it does. With R2 providing a frequency-based filtration unit that allows it to go down, all of these guys go down to ground at the very end with a ground connection that leads back over to the negative terminal of my battery clip. Is what that is. So we're going to assemble some of these together. Actually, right now on my circuit component here. So I might be flipping back and forth between these screens a little bit here. That might hopefully it doesn't jostle everyone around with it too much. The overall layout of this, actually, that's probably one thing I can actually show really quick here, just so you can kind of see what that looks like. Where are you here? Are you over here? Hi, how you doing? There you go. The layout of this guy. The way that this layout looks, and I'll try to switch to more of a photo view of what this looks like here. Actually, maybe the 3D view would probably be best in terms of what this looks like. Now, I don't have blue. I'm going to switch it to green because my board is green. Hello, green. Can you switch over to green? Hi, green. And then I actually have silver contacts. I do not have gold on my contacts. And here what you have is the actual 3D view of the board as it's been fabricated over by the folks at JLC PCB. It was a great company that I've been ordering from a whole bunch of times. So on this circuit board, here is where C1, one of the filter capacitors for the top part of the circuit is going to be. And then we have a C2 and a C3 capacitor that are actually going to go to the microphone here. And then R2, at least I think it's R2. Is it R2? Yeah, R2 is going to be this guy that's over here on the bottom side part of the microphone. This guy right here is what we would call a test pad, and then R1's not going to have anything attached to it, although maybe down at the end I might attach a little bit of something for fun to it, just like a large resistor or something like that. Otherwise it'll look lonely. We don't want that to happen now, do we? So now you might be saying to yourself, hey, there's a bunch of other stuff over there. That looks kind of cool, right? You know, that's what it does. Where is the battery? Well, the battery happens to be located on the back side. It's this guy that's right here, mounted over this hole that's over here. And these holes are in slightly different spaces. This might be a slightly newer version of this circuit board. I'm actually not quite certain about. Yeah, it actually is a slightly newer version of this circuit. But no matter how, those are actually mounting holes for some of the tools that I've got on the college's laboratory, being able to mount this thing into place. The battery is actually on the back. Now, for reasons of keeping this thing flat on the ground or on my mat for doing hand soldering, I'm actually going to not solder the battery until close to the end when I have everything else attached to it. And the microphone, as I've demonstrated in the video, the lid comes off pretty easily, and there's actually going to be one of the chips that might be a little bit of a problem that we have to apply a little bit of some excess heat to get it down quite right, and that's U2. But we'll get to that. We'll get to U2 in a slightly different video. Let's solder some of these components on here, shall we? So we're going to put the board underneath here, and let's start with some of the capacitors for what it is that we have here. Now, the capacitors that I have are 1 microfarad capacitor, and they actually come on what we call tape and reel. Now, this old-looking thing, which kind of, I guess in some ways, this kind of looks like film strip, is what this is. Film strip, film. That thing that used to be on film, that's now videos, that doesn't get recorded on film anymore. Film is a lost art, it's unfortunately. Automatic machines that place these parts down have parts that come in on what we call tape and reel, is what this is. And we're going to take some of the parts out of this tape and reel. This tape and reel, which underneath the microscope, very much does look like it could be loaded up onto a film strip. In fact, I'll show that in a later video in terms of what that actually looks like. Now you got the sprocket holes that are here. The parts are actually housed in here, and there is a small bit of a plastic coating. This is what we call embossed tape and reel. is what this is, because the whole thing is essentially made out of plastic. This thing just sort of peels off right here. And I'm gonna take 3 of them off. Is what I'm gonna do. They pop out of their little holes that they got there. Not their little holes, their little homes is what they got. And now I've got 1, 2, and 3 capacitors associated with this. Egads, where is my wrist strap to this? Oh my goodness, look at that. That's terrible. That's what this is. Got myself a little wrist strap here. All right. So making sure that I'm controlling my electrostatic discharge as I'm going to be connecting these guys over to what it is I'll be connecting them over to. So the capacitors are all going to be connected. Excuse me. Sorry about that. Can I move through here real quickly? Thank you. I've got C1 located right here. There is a small error, if you will, of the silkscreen layer of the Triforce. One of them is on here. Minor design flaw. And then if we move over just a little bit, we see that C2 and C3 are located right here. I'm going to turn the board over so that this is going to be in this direction here. And now what I'm going to do is I'm going to apply some tin over to each one of these pads here and attach the component down to it. So let's start with C1. This is a lead-based solder material that we're using for this, which is sort of like your easiest material to start working with. This is what we exactly recommend some of our other students kind of work with when they're first starting projects out for the first time. Oh my goodness, look at that! Look what's on there. You see that? There's a hairy beast showing up on there. Well, I got some fluxing agent on my hand here, so I'm going to cover both the pads over. Take the soldering iron, which I have currently set to 600 degrees Fahrenheit, which is kind of over from a previous video. I have a nice tin tip, and I'm going to apply some solder down to that guy here. Come on over to C2. Very similarly, actually, on both C3 and C2, I'm going to apply a generous amount of fluxing agent onto each one of those, although C3 was kind of done a little bit off the camera there. And I'm going to come down and apply the left-hand side. One person actually asked me one time, how do you develop the skill and practice of being able to apply some of this stuff too? And honestly, some of this really just comes from repetition. It really just comes from sitting down, repeatedly putting down parts over and over again onto a circuit board like this, and just creating little hobby projects for yourself. Also does come from having the right tools. I mean, even like a basic screwdriver or a basic like simple drill bit. One might say that if you have a bad drill bit, that will ultimately not make it easy to drill things into place. Notice I have left that on the pad for a long period of time, allowing the capacitor to sort of get heated up so that some of the solder material actually kind of wicks up the surface of the capacitor. A very important thing to do, because if you don't do that by doing this by hand here, and I'll kind of demonstrate by C3 here, if you don't allow that to happen, I'm going to try to get a side profile shot of kind of what this looks like. So the one that is soldered correctly is this one here. And notice that the kind of meniscus, there's a little bit of a curvature that goes up onto the side. It creeps up the side of the capacitor and forms a nice little bond. Might even be a little bit better if I apply a little bit some solder paste, but look at this guy. It hasn't really crept up at all. It's just kind of stuck there, and that's because the capacitor didn't have enough time for it to heat itself up and allow the solder to kind of curl up to the side of it. Now, if I come on in here with my soldering iron and I let this sit here for just a little bit longer, pardon me, I'm just kind of going to try and do this as best as I can. One can see that the solder just kind of goes right up the side of that. Oof, excuse me, I'm sorry about that. That's because I'm using my other hand to hold this guy down. Pardon me. Can I come on over here for a second? I'm going to put this down because oof, that was a little bit, excuse me, of an oof is what that was. Well, that's not too bad. It's a little bit off center, but it's ultimately not too bad. We'll see if we can fix this by applying a little bit of some U here. letting you come up. Oh, it's soldered down onto the other side to it here. So I'm just going to kind of roll with this one the way that it is. Come over here to C1. Here we go. I'm going to take my last remaining capacitor, which is this guy right here, with my soldering iron in my left hand, heat up the solder, and then take the capacitor. These capacitors are not polarized, which means that it doesn't matter which way I connect the capacitor to the circuit board. Certain capacitors are polarized, indicated by a polarity marking somewhere on the side of the capacitor. So something to be wary of in case there's something that's there. The size of these capacitors, so these are what we would call 0805 capacitors. You see it kind of really nicely creep up the side of the capacitor. The reason these are called 0805 capacitors is because the capacitor in its length and width, like not counting the height, but the length and the width is 0.08 inches by 0.05 inches. And there is a metric equivalent for that. I don't unfortunately know that off the top of my head, and I really should. There's so many parts of the world that are moving towards a metric, including the electronic industry. That is ugly. Excuse me. Sorry about that. Oof. There we go. And then the last capacitor, which is hopefully on the screen right here. Really likes the way that solder just kind of creeps up the side of the capacitor. That's really what you kind of want it to see. You don't want to have a bad capacitor joint. There we go. That's crept up the side quite nicely. So it's there, and there you have the capacitors are all connected. We are also going to work on connecting R2, which is, according to my schematic, was a 1 kiloohm resistor. Killi being what we call an engineering prefix. And the killi is essentially an engineering prefix which is often represented as a letter K. I've seen capital and lowercase. I myself have always kind of thought about it as either or, because none of the other prefixes really use it. So there probably is a correct. If you know the correct one, if it's upper or lowercase k, help me out by throwing that into the comments at some point there, because I'm actually not quite certain off the top of my head, and I will take a look at that later. So now let's take a. I'm kind of using up a little bit of the scrap parts of my solder, so I've got like little parts of solder kind of. Just kind of floating around here. So I'm going to come down to R2 and tin the side of R2 just a little bit, and the fluxing agent activated. Now, here's a big question. I have all sorts of electronic components that are hanging around. This is supposed to be a 1 kiloohm component. That says 475, so that is not the right one. I'm going to put my soldering iron down so I don't accidentally burn something. So that would mean that instead of it being you, that would mean that it must be you. Is that right? No, you are a completely blank component here. Do I have a 1 kiloohm resistor? I thought I just kind of made a general grab of all the components that I needed in advance to it right there, but clearly I haven't. Here we go. Here we go. I've got it here. I found it. That's what happens when you're working with electronics after a little while. You wind up having things all over the place is what you wind up kind of having to it there. There we go. I'm just going to kind of plop you down. Is that okay there? Can you stay right there for a second? I'm going to grab the soldering iron with my tweezers in my right hand. I am right-handed. I know a lot of people who are very, very good on the ambidextrous side of how they connect up some of these components together here. So here, let's attach the resistor, and gee golly, let me put it so that it's the correct orientation, so that the numbers are in the correct orientation. There we go. It is 102, as we've learned from the kind of one of the last videos that we had here, that represents a 1 0 and then finally followed by 2 zeros. That is a 1000 ohm resistor is what that is here. All right, and then we kind of come across on the last one right there. Normally you don't want to have a blob of solder on the end of it right there, but I'm going to kind of heat it up anyway, just to make sure that the small circuit components, all my resistors on this circuit board, by the way, are 0603 in their overall size, which is kind of like your above average standard size surface mount component that's there. Now, the last thing that I wanted to attach is the switch, and I'm just actually looking around right now. It appears that I have forgotten to grab the switch. So just bear with me one moment. Slightly off screen, minor difficulties. Excuse me, pardon me, sorry. Excuse me. You okay there? Excuse me. Hi. Hi, there we go. Here we go. I got all my components here. That sound that you kind of hear in the background is the mascot of the laboratory, the lab, if you will. He's down on the floor sleeping right now. It's all he ever really does. He's a yellow Labrador retriever who likes to sleep on the ground, and likes to do what it is that he does. Maybe we'll bring him onto one of these videos here at some point. Have a little cute puppy mascot. He's not puppy. He's 11 years old. He's a big old dog is what he is. So I've got the push button switch that is actually going to go on this switch connection right here. You see that? I got a little switch connection is what I've got here. There we go. Cool. That's kind of neat. So this switch actually is meant to fit right in this spot right here. See that? Kind of meant to fit to it right there. This is a more of a tactile switch, so I have to hold this down in order for the switch to be activated. But I need to solder it down first to this here. And the way that I'm going to do that is the same way I did the resistors. You put one side down, and then you put all of the other sides down. So I'm going to apply fluxing agent to all 4 sides, all 4 corners, because this is a this is a multi-pin switch. And a single pole, double throw, single pole, something like that with it on there. I'll have to look that up. Put that in the comments as well. I should probably know a little bit of stuff like that, a little bit of stuff like this. Okay, now I got my solder, so I'm going to come onto the upper left here and put some tinning of the pads. Geez, I'm trying to hold that with a pair of tweezers, and that did not work out well for me. So running out, that one's just running a little bit short is all that it is. I might grab a different pair of tweezers to attach that guy. So you all still see what I'm doing here. I got my soldering iron that is now wetting the surface of you. I'm going to place the switch and let that sit in there for just a little bit of time. Kind of try and watch some of the solder creep up the leg of the switch there just a little bit. I'm going to try to, we really want the switch to be sort of hot enough for the solder to make sure that it has good contact to it, and that sure looks like it does to me. Let me grab I'll try grabbing the same solder wire here again. So now I'm going to come down to the other switch here. There we go. A little bit on that one right there. I'm going to turn this around so that the switch is now on the bottom side of the connector. A lot of times, I have to say, a lot of times when it comes to assembling these circuits, it comes to orientation is what it does. It really does come down often to orientation of the device. I'm going to put a lot down on these guys right there. The mechanical switch, due to its mechanical nature, this is the thing I'm going to be pushing up and down with on my thumb. So I would like this to be a little bit more sturdier than all the rest of the components for it here. So I might actually just double check to make sure that I've got enough solder down on all of the component sides, just to make sure that there's a plentiful amount here. I think what I've got there is fine. I'm going to add just a little bit more to the top pins here, just in case. There we go. That's looking good. Okay, so what we've got soldered into place right now on the board, we have got C1, C2, and C3 soldered. The switch has been soldered, and R2 has been soldered down to the circuit board. So we're going to leave U1 for a little bit later on, as well as the battery clip. We're going to leave that for a little bit later on as well. All right, folks, if you've got any comments on ways to improve or deprove this circuit, or if you're interested and just want to leave a comment just to say, hi, this is helpful, or this is really weird, or anything like that, whatever you'd like to do. So thanks very much for stopping by, and we'll see you on the next video here. Bye-bye.